Hi, welcome back to Mat120, section 1.5, page 48. We're going to discuss intersections, unions, and compound inequalities. So let's find out what an intersection is. An intersection is when we have two sets and we have elements that are common to both of them. They must be in both the things. Let me tell you the difference between and or. Let's suppose you're washing the dishes. You're come home and your mom says, you tell your mom, I'm going to wash the dishes and I'm going to wash the car. I'm going to wash the dishes and I'm going to wash the car. That means you have to do both of those things. You said you're going to do that and. So an and is kind of a descriptor that says it has to be in both sets. It has to be in washing the car and it has to be in washing the dishes. And if you tell your mom, I'm going to wash the car or I'm going to wash the dishes, means that you're going to do just maybe one of those. You could do both, but you might just do one of those. So an or statement is more flexible. An and statement means it has to be in both. So let me show you what that means. That's what we call an intersection. So if we had say this set, let me give you a set of numbers here. We have the set 1, 2, 3, 4, 5. Easy enough, huh? And we want to intersect that. Intersection means we want an and statement. And we designate an intersection. Looks sort of like an A. If we put a line through there, it would be an A. With this set, another set, we call this set B, and that was -2, -1, 0, 1, 2, 3. The intersection of these two sets is the set where just the elements that are common to both of them. Like both of these sets have a 1. They share this common number, 1. They both have a 2. They both have a 3. They have other numbers. This has a 4 and a 5. This has a 0, -1, 2, -2. But we want just the elements that are common. We would say that this is the intersection of these two sets. And we would designate it as the intersection is equal to 1, because it's in both of them, 2, both of them, 3. So an intersection must be a point or a number that's in both sets to be an intersection. Another way of describing this would be you had this set right here. We're read like 4, 5. We'll put it backwards. 3, 2, 1. Like that. And then we had this other set that was, we'll put that one starting with -2. We read that one backwards. It had -2, -1, 0, and then it had these same numbers in it. So it's the intersection where those collided. That's common to both sets. It belongs to this set. Hey, I belong to set A. But I also belong to set B. I'm in both sets. So it has to be something that's common to both sets. That's what we mean by an intersection. So let's take a look at a graph here. Suppose we have this graph, -2 is less than x. And we have another graph, x is less than 1. And we want to find the intersection of these two. Sometimes we call this the conjunction or the intersection. And conjunctive in English is an and or a but statement. So this is what we call conjunctive, or I like to call it intersection. So let's graph this first one. Well, before I graph it, I want to rearrange it because I don't like I like my variable to come first. So I'm going to switch this. If negative 2 is smaller than x, then x must be bigger than negative 2. So on a number line, I'm going to graph that. Here's negative 2. I'm going to put it up here. Here's negative 2. And it's open circle. And it's numbers that are greater than negative 2. Now on another graph, I'm going to graph x is less than 1. Okay, so x is less than 1. So I'm going to graph that one. And here's 1. I'm going to draw it through these two. Project it down. Here's 1. And what would that be? That'd be an open circle 2 also. And it's going this way. Okay, the intersection is the common points, a point that's also in this set and in the other set. This point is only in one set, so we project that down as an open point. But these are filled up. And if we project down, but then again, this point is only in one set, it's not in the other one, so this is open. So this is what we would call the intersection of those two sets. I just draw it like that. And we could also have done it with, the parentheses type thing using interval notation like that. I think most of us are used to this notation, and that's fine. It really doesn't matter. So that would be the intersection of these two sets. It would be negative 2 is less than x and x is less than 1. Now, I'm going to show you a little trick. The reason they wrote this way is we can push this together. Let me write it down here. Then an x. Okay, you see how they have it, x and x? Okay, we can push those together. And sometimes we could write this intersection as negative 2 is less than x. We just put this as all one big X is less than 1. Now, we want to write this with less than symbols, and we want them both going in the same direction. That's why they wrote it this way. To graph it, it's a little bit easier to rewrite it, but we can combine this into, and this is what we call a compound inequality. It's saying negative 2 is, it's read as negative 2 is less than x, and x is less than 1. That's how we read it. Or we can read it as x is between, right here's your x, somewhere between negative 2 and 1, there's an x. All right, so that's what we mean by that kind of a statement. Let's see if we can do another one here, a little bit more complicated one, and see if we can make sense. Let's try this one. Negative 1 is less than or equal to 2x plus 5, and 2x plus 5 is greater than 13. Now, because both these inequalities are the same, we can punch them together. We can push it together. And they both have less than symbols. So negative 1 is less than or equal to 2x plus 5, and 2x plus 5 is less than 13. Now, how do we solve it? Well, I'm going to show you a little shortcut for solving it. We don't work from the inside out. Pretend like this maybe isn't even there. So if we were going to solve this problem, we'd get rid of this 5, huh? We'd subtract 5 from both sides. Well, we're going to subtract 5 or add a negative 5 to each element here. Negative 5 to this term, negative 5 here, negative 5 here. And we're adding that. So that's negative 6 is less than or equal to 2x is less than or equal to 8. what we're trying to do is get the x all by itself. Now, to get rid of this 2, we're going to divide. If this was 2x is less than 8, we would just divide by 2. So we're going to divide everything by 2. I'm going to put a little slanted line to show division. So negative 3 is less than or equal to x is less than 4. Now when I go to graph it, negative 3, I'm going to use a solid dot because it's less than or equal to. And 4, I'm going to use a open dot, and it's anything in between. So the points have to be in this set and in this set. And these are the only numbers that are in both sets. Negative 3 is in both sets, and then anything close to 4 is in both sets. So that's how we do it, and we wouldn't have to draw separate number lines. Okay? Well, you're saying, well, what if they're not the same? Well, let's try another one. How about 2x minus 5 is less than, it's greater than, let's write it, greater than or equal to negative 3. And, see, that's an intersection right away. 5x plus 2 is greater than or equal to 17. So if we want to do this one, it's a little bit more different because we got to do each problem separate. So we're going to bring this 5 over to the other side, working with separate problems. Add 5 to it. I just read it this way. I could also use my shortcut, no problem, and divide both sides by 2. X is now greater or equal to 1. I don't have to switch it because I'm dividing by a positive number. How about over here? I'm going to subtract 2 from both sides. 5x is, these canceled, greater than or equal to 15, and I'm going to divide both sides by 5. X is greater than or equal to 3. Well, here's kind of an interesting one. Let's see what happens when we go to graph it. Let's draw 3 number lines, one for greater than 1, one for greater than 3, and one for our intersection. And here's 0. Okay, this one says we're going to start at 1. I'm going to start right here. It is a solid dot. Start exactly at 1, and I'm going to go, let's go ahead and label these 1, 2, 3, etc. So let's put a 4. Okay, I'm going to go this way. So it's all those numbers. Now this one says I'm starting at 3, and I'm going in the same direction. So what's the intersection? What is the intersection of these two? The intersection is the points they have in common. This doesn't have any points. In other words, you need a point in, let us say, and B. You need a point that's common in A and common in B. They both share the same number 3, so we can project that down. They also share all these other points. We can project those down. So it's anything from 3 on. Most of the time, intersections are between 2 points, but it could be a situation like this. But they have to have shared points. They have to be a point here and a point down here to give us a point all the way down. Bing, bing, bing. Bing, 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 bing. Nothing there. There's nothing to catch it. See, they had to catch each other. All right, so that's what we mean by an intersection. We can also have an intersection where they don't intersect at all. One's going one way, one's going the other, and there is no intersection at all, and then that sometimes happens too. So it's possible that maybe both of these were going in the same direction, both of them came out the same answer, or we have one going like this, and then another one going like that, and they have what we call an empty intersection. For instance, we had this set A, 1, 2, 3, and we have the set B, 4, 5, 6. You see, they have nothing in common. When that happens, we draw this symbol, the no set. No. There is no answer. The no set. So it's like a 0 with a slash through it. That's why sometimes you don't want to write your zeros with slashes through. It means that there's nothing there. Where at 0, even though it's kind of means nothing, there is something. You don't want to draw it. Sometimes we also draw a set notation like this, and we put nothing in there. You don't want to put the no set in front of there because that means you have something. So usually it's easier to draw this symbol. And that means nothing. Not a thing. Okay, let's try one more. I got a little bit of room here. Here's one. 3 is less than 5 minus 2x is less than 7. Okay, we want to solve this. Start from inside. Let's get rid of this 5. We're going to subtract a 5 from everything. On this one, it's probably easier not to write shortcuts, you know. Sometimes they're good, but sometimes they can get confused. Now, again, we're going to start inside. We want to get rid of the -2 by dividing. We're going to move something or add something to both sides, a -5. Now we're going to divide everything by -2. And this guy also. So that gives me 1 is less than or equal to x is less than or equal to -1. Oh, is that true? No, because what I did here is I divided by a -2. And what happens when you divide by a negative, it switches the symbol, doesn't it? So we want this symbol right here to switch. This needs to be greater than or equal to, greater than or equal to. But we usually don't write these with greater than or equal to. So what I kind of think of this is kind of coming around a bend. Let's just turn all these around. This becomes -1. As this goes around, greater than symbol, greater, greater. See how it's changing as it comes around here? I don't know if you can see that so good. But as it comes around here, it changes to a less than or equal to. X comes around here. This comes around, less than or equal, and then the 1 comes around. So I kind of think of it as going around like a circle here, kind of like half circle. It's kind of coming around. And as that symbol comes around, it's turning itself into a less than symbol. Greater is becoming less than. That's the way I imagine it. It's probably not very mathematically sound, but that's how I envision it. So it helped me remember it okay. If we were to graph this thing, let's graph this, then we would graph this one. And also when this came around, let's see, when we run around this, this should have been, the one would have been, this would have been open. It shouldn't have been equal there. So when we go to graph it, it would be -1 would be open and 1 would be closed. It would be in between. Or we could say it this way, -1, comma, 1 with interval notation. Now we can do it all different ways. We're flexible. Okay, the next thing is a union. A union is a collection of all objects. So let's say we have this set here. We could have done, let's do the original set. Flipping around here. Okay, remember our original set was 1, 2, 3, 4, 5. And our other set was -2, -1, 0, 1, 2, 3. But now instead of an intersection, we're going to do a union. A union is an or statement. You could have written the word or. So in an or statement or a union, remember only one part has to be true. They could both be true. So if we look at this, they do have some things in common, but we're concerned with just everything that's in it. So yeah, it's nice that they all both have 1, 2, and 3. We could write that down. And we'll put the union is. But they also have some things that aren't in there. They have a 4 and a 5, and a -2 and a -1. You know, you put these in order, I will call it prettier, but a union is everything that's in one set and the other set. We don't duplicate them. If they happen once here and happen here, we usually just write them down once. But it's the union of all those numbers, all the numbers that they have in common. So a union could include the intersections, but it also is all the numbers that they have in common. So let's take a look at a union and see if we can do one. So an and statement is a lot different from an or statement. Here's one. 2x minus 3 is greater than 1, or, wait a minute. The page here. Or, let me do a different one, I'm sorry. 7 plus 2x is less than -1, or 13 minus 5x is less than 3. Okay, so we're going to do each one of these separate, and then we're going to see what happens. We're going to solve this problem because you can't punch them together. Can you push them together? No, they can't. I mean, this is like totally different. So let's bring the 7 over. Minus 7 minus 7. 2x is still less than -8. Divide by 2. X is less than -4. With I hold up, yes, I'm dividing by a positive. Or, let's put a U here for or. On this one, I'm going to bring the 13 over to the other side. I'm going to subtract 13 from both sides, or add a -13. Make sure you bring down the negative sign. Is less than or equal to -10. Now I'm going to divide by -5. And that is going to cause this to switch. X, and this would be 2. All right, so let's take a look at these on separate graphs. This is x is less than -4. This is x is greater than or equal to 2. And this would be the union of those two, or the or statement. So I'm going to project a line through here, -4. And somewhere in here there's a 0, and somewhere there's a 2. Okay, on my first graph, it says it's less than -4. So I'm going to put an open circle, and I'm going this way. On my next graph, it says it's greater than or equal to 2. I'm going to put a solid down and going this way. Now, if this was an intersection, we can see there's no intersection at all. But on a union, it's all the points. They don't have to be, on an intersection, there had to be points here and points here. On a union, that doesn't hold true. As long as there's one point, it's an answer. As long as there's one point. So when we project this down, the union would look like this. All these points and all these points. So that's the union. The union is this answer right here. So I know you're getting ahead of me. You're saying, oh, Mr. Mitchell, how do we write that as in interval notation? Well, in interval notation, it would look like this. Negative infinity to negative 4. And then it's close to negative 4. It doesn't quite hit it. Or you could write union. And it starts exactly at 2. And it ends at positive infinity. And that's how we would write it as a interval notation. Does this where it starts, it kind of stops, takes a little rest, gets some lunch, visits, plays some baseball, and then it picks up again, starts with a 2 and keeps on going. So that's how we would do an or statement. Kind of interesting now. So we could write this as I shouldn't have put an intersection. What I do? This is a union. A union. What was I thinking? Or an or statement. I don't know why I put an intersection. Intersections on the brain. Okay, let's try another one. Negative 2 is negative 2x minus 5 is less than negative 2, or x minus 3 is less than negative 10. Okay, add 5, add 5. Can't push them together. You couldn't push them together. It's an or statement. An or statement, you can only push them together if it's an and statement or an intersection. So we're adding 5 to both sides. Negative 2x is less than 3, if I'm right, I think. And then I'm going to divide both sides by negative 2. I'm going to do the old switcheroonie, put the negative on the top. Yeah, divided by negative. Union. On this one, I'm just going to add 3 to both sides. X is not switch, 7, negative 7. All right, so let's see what the heck happens here. This could, let's change this to a negative 1.5. It might be easier to think of it that way, huh? So let's draw a number line, and a number line, and a number line. X is n, so later on as you get better, you might not have to draw on the number lines. Negative 7, and the union of these two. So right here is 0, negative 1.5, negative 7. Okay, so this says it's greater than, well, this is kind of like the last one we did, huh? It's greater than 1.5. Going this way. This one's saying it's less than negative 7. Going this way. And then we're just going to project them all down. So that's nothing fancy. So it would be negative infinity to negative 7. Union negative 1.5 to infinity and beyond. Okay. Then we get rid of that way. All right, I thought it was going to come out interesting, but it didn't. One last one, and then we're good for the road. Okay. 3x minus 11 is less than 4, or 4x plus 9 is greater or equal to 1. All right. Solve them separately. 3x is less than 15. X is less than 5. No switcheroonie. Or add a negative 9. 4x is greater than -8. Don't try to do too much work in your head. And then by 4, no switcheroonie either. X is greater than or equal to -2. Let's see what happens on this one. X is greater or equal to -2. X is less than 5. The union. Here we have, let's put -2 over here. Here we have 5 over here. So greater than -2, it's going to be greater or equal. Going this way. This one says it's less than 5. Open. The answer. We're going to project down all the points. All right. Even if there's only one point, we project it down on a union. All these points get brought down. If there's a point here and a point here, that's fine. It's still a solid point. If there's an open point and a solid point, it doesn't matter. See, on an intersection, you would just bring down, you would keep it open. But on this one, it's going to become solid. So looks like it's everything. It's all real numbers. This is a symbol for R, real numbers. It's everything. If we wanted a designated interval notation, it would be from -infinity to positive infinity, like that. And that would be interval notation. Or you could just say all numbers. All real numbers. All right. So that's kind of the idea behind these. Hope you enjoyed it. And we will see you next time.